The question is, how do you calculate deformation of a statically indeterminate axially loaded 1D rod? Let's start by defining what we mean by statically indeterminate 1D rod. Here is how we would know if a given problem is statically indeterminate or not. In a given problem, let n sub u be the number of unknown support reactions and n sub e is the number of equilibrium equations that can be written down. If nu is equal to ne, that is, number of unknowns and number of equations are equal to each other, the problem is statically determinate. So these are the kind of problem we've been dealing with so far, right? On the other hand, if nu is greater than ne, that means number of unknowns are more than the number of equations we can write down, then the problem is statically indeterminate. We don't have enough equations to solve for all of the unknowns on the basis of equilibrium alone. So let's look at some examples, and here's one. You might recognize this. This is based on a problem that I have used in the discussions in some of the previous videos. We have a 1D rod with 3 segments, each potentially having different cross-sectional areas and properties and lengths. The rod is fixed at point A, but it has a free end at point D. So if we were to cut the rod out of the support and draw the free body diagram for it, we need to mark the support reaction at point A, right? Calling that as AX, we see the number of unknowns in this problem, Nu, is 1. The number of equilibrium equations we can write down for this problem is also 1, which is the force balance equation in the horizontal direction. Keep in mind that the equilibrium equations we write down must be meaningful. For example, you could say, well, I can write down one equation in the x direction, one equation in the y direction, one equation in the z direction, and so on, right? But in this problem, forces are all in the x direction, and therefore the equations in the y and z directions are not meaningful because they will not have any forces in them. Alright, so we have Nu equals 1, Ne equals 1, and therefore Nu and Ne are equal to each other, and therefore by definition this is a statically determinate problem. Here's a summary of the equations we used in one of the earlier videos to find the displacement of a point on the beam. We calculate the deformation of each of the 3 segments using these equations. If we consider the first equation right here, NAB is the axial force within segment A to B, LAB is the length of the segment AB, EAB is the Young's modulus of the segment AB, and little a, AB, is the cross-sectional area of the segment AB. So this expression allows you to calculate the deformation of the segment AB, and these equations are similar. In performing these calculations, we'll stick to a sign convention. Typically, tensile forces would be positive, and therefore tensions would be positive. Once we have this deformation, then we can calculate the displacement of a given point, like point B, C, or D, using one of these equations, right? In my example number 2, I'm going to take the problem we considered in the earlier slide and put a support at point D. In other words, the beam is held between 2 fixed supports, one at point A and another at point D. Now you put the external forces on the beam. There's going to be a support reaction at point A and there's going to be a support reaction at point D, right? Therefore, the number of unknowns now is 2, but the equilibrium equation is still number 1, because only equation that we can write down is the sum of the forces in the horizontal direction, right? And therefore Ne is still 1, and therefore Nu is greater than Ne. By definition, this is a statically indeterminate problem. You don't have enough equations to solve for the 2 unknowns. We only have 1 equation, 2 unknowns. We need 1 more equation. The required additional equation is the following, which is also called the displacement compatibility equation. The equation is that the displacement at point D is 0. We have a fixed support at point D, right? And therefore the displacement at that point has to be equal to 0. We follow the same approach as before for calculating the displacement of point D. In other words, we go ahead and calculate the deformation of segment AB, segment BC, segment CD, right? And then we sum up the three algebraically with some sign convention in mind in order to express the displacement at point D, right? And of course, we are not going to be able to find numerical values at this point because we have two unknowns, AX and DX, right? So these equations are going to have these unknowns in them. But we have two equations now, two unknowns, two equations. One equation comes from the equilibrium equation. The other is this compatibility equation. So we have two equations, therefore we can solve for them. So once we solve for them, we will have numerical values for the support reactions, and then we can come back and substitute them in these deformation equations in order to calculate the displacement of various points like points B and C, the two interior points. So that's how you solve problems like this. So in this approach, we start from point A, the fixed point A, express the displacement of point D and set it to 0, right? Alternatively, you could start from point D, express the displacement of point A and set that to 0. So you can do it either way. There are two ways in which the displacement compatibility is enforced. Just to show you the similarities and differences between the two methods, let me first turn this into a more generalized problem by putting a force P1 over here and a force P2 at point C. In the first method, we approach this problem as is. So I'll just call this the direct method for now. Let me first introduce some simplified notations here. Let's say alpha AB is defined as LAB divided by little aab times EAB. Alpha BC and alpha CD are similarly defined. Now sectioning within each of these segments AB, BC and CD and marking the internal forces as tensile forces, we get these for the internal forces in these segments. For example, if I section it over here and mark the internal forces as tensile force, your NAB is going to be going to the left, right, directed to the left. And by equilibrium equation, we know NAB then should be the sum of all the forces going to the right. That will be dx plus P1 plus P2, right? So that's what I have over here. And similarly, if you section it here, you get this, and if you section it over here and still consider the right side, you get this, right? The deformations of each of the sections are then given by these equations. Displacement of point D relative to point A is given by this equation, and we know the displacement of point D relative to point A must be equal to 0, right? So that's our compatibility equation. Now combining all of these equations, we get this expression for dx, and then using the equilibrium equation, we get this expression for ax. So this is how we solve for both unknown reactions, ax and dx. Now we can evaluate numerical values for the deformations of the segments, and then we can calculate displacements of any point on the beam, like point B or point C. The second method is called the force method, also called the flexibility method. This method is based on the use of the principle of superposition. The principle of superposition is something that could be used in linear problems. For example, the material behavior has to be linear. So obviously linear elastic material behavior would qualify the problem for the use of principle of superposition. In terms of precise steps, this is what we do. First, we identify the redundant support reactions. So what do they mean by redundant support reactions? Well, now going back and looking at this example problem we are considering here for our discussion, right? We have two unknowns, right? Two unknown reactions. There's one at point A, one at point D. But we can only write down one equilibrium equation for this problem, right? So we say there's one too many reactions here, all right? In other words, the difference between the number of unknowns and the number of equilibrium equations is what is called the number of redundants. So one of these reactions is a redundant reaction. In some problems, there could be more than one redundant. The second step is to split the problem with and without the redundants on the basis of the principle of superposition as follows. You see three pictures here, right? So in the first picture, what we have done is we have removed this reaction at point D, because we're going to treat that as our redundant. There are two reactions and one of those is redundant, right? So you're going to treat this as the redundant and remove it. When you remove it, there's just one reaction, and therefore this is a statically determinate problem, right? In the second picture, we take this reaction and put that back in there like an external force, all right? But we remove these external forces P1 and P2. So this problem is still a statically determinate problem with the reaction being applied as the external force. Now we add this to this in order to get the original problem, where we have both the external forces P1, P2 and the reaction dx, right? So this is what is possible by the principle of superposition. Now we solve each of these statically determinate problem separately. So like we did before, first we're going to find the internal forces in these segments. So obviously we had to section them within these segments, and we're going to consider the right side. So if you do, this is what you get for the internal forces, and then the deformations would be these, and the displacement of point D would be this, right? So I'm putting a prime over this quantity because these are not the actual forces or displacements of the real problem, right? These quantities go with this particular problem. Now you repeat this for the second problem, all right? We find the internal forces, deformations of each segment, and sum them up to come up with the displacement of point D. Now since this plus this is this, right? And that goes for the displacement as well. And therefore, the displacement of point D of the real problem is actually UD prime, the one that comes from the first problem, and UD double prime, the one that comes from the second problem. Now we enforce compatibility, displacement compatibility, which is the displacement of point D for this real problem must be equal to 0, right? Now you use these expressions to expand this equation and evaluate dx. And dx works out to be this. And if you compare this with what we got in the earlier slide by method number 1, it's the same. Having found a value for the redundant reaction dx, now we can kind of go back and calculate the displacements of the interior points B and C as shown over here. We're still using the principle of superposition, and therefore the displacement of point B should be equal to deformation of AB coming from the first problem here and the deformation of AB coming from the second problem here. And that simplifies to this. And similarly, the displacement of point C is the deformations of AB from problem 1 and 2 and the deformations of BC from problem 1 and 2. And that simplifies to this. Now, like we did in method 1, you use the equilibrium equation to find the reaction AX. That's it, we have solved the entire problem. Here's my third example. We consider the same problem we considered in the earlier example. The difference is, instead of having the fixed support right at point D, it is in the vicinity of point D. In other words, there is a gap or delta gap between point D and this fixed point. Supposing, say, we treat this problem like in example number 1. In other words, we treat point D as a free end and go ahead and calculate the displacement of point D. Let's say that displacement is U sub D. Supposing, say, U sub D is greater than delta gap. What's going to happen? Point D is going to try to move beyond that fixed point, but the fixed point does not allow that to happen, right? And this will lead to the development of a reaction at point D. In other words, we're going to end up having two support reactions, AX and DX, like in example number 2. The problem becomes a statically indeterminate problem. We need one more equation to solve for both unknowns, and we approach this problem in exactly the same way we approached example number 2. Our displacement compatibility equation is this, a little different from what we had in example number 2. In example number 2, we said UD is 0, right? But here it's not 0, but here it's going to be delta gap. That's it. Everything else remains the same. We go ahead and solve for the two unknowns first, and then we come back and calculate the deformations and the displacements of interior points. So these are the sort of statically indeterminate problems we are interested here. And you can see in these problems, the problems become statically indeterminate due to mechanical restraints. In this second example, we had a fixed support at point D. In this example, the third example, we have a fixed point in the vicinity so that the deformation is going to try to close the gap. In one of the future videos, we'll consider the thermal effects. We will find that there's a lot of similarities between these mechanical problems and the thermal problems.